Thank you. So this talk is about points 2 analysis. It's work done together with Nick Hollingam, who is also in the audience over there, and Bernard Scholz from Oracle Labs in Brisbane. So background, points 2 is static analysis. There are many analysis clients, such as security optimization and verification. And there's a significant body of research on this topic for the last 20 years or so. So what we did fits into this kind of multi-dimensional space you could draw to classify this research as follows. Our analysis is field sensitive, which is not very sensitive by today's standards, but I explain in a moment why we did this. And that's really the problem precision. Once you have a problem precision, you can also ask how precise your solution is with respect to this problem. And here we are aiming for a precise solution. And the focus of this work is really to push performance and complexity. And there are really two aspects to this. One is the worst case complexity, it's the more theoretical considerations. The other one is more practical consideration of actual performance in practice. And we also provide parameterized complexity analysis that underpins the practical results we achieve. So context insensitive points 2 analysis to solve problems. It is a fair question because most of the recent research has focused on context sensitivity. So this project was really triggered by some evaluation of existing analysis tools inside Oracle Labs, which had the aim of including points 2 analysis into the nightly builds for the OpenJDK, and that OpenJDK is a very, very large data set. So if you draw or if you extract graph-based models, and you end up with a graph that has over 1.5 million vertices and a similar number of edges. And if you then compute points 2, you get over 1 billion records that associate variables with objects. So the problem here is really scalability, and none of the tools, none of the algorithms available at the time scaled sufficiently to do this kind of analysis on this real-world data set. So the problem, just to quickly repeat this, most people in the audience will be familiar with this. So we have a representation of objects which we abstract through allocation sites. So I call them H for heap objects here. Then we have those allocation edges where we assign this to variables, and then we have assignments between variables. So we get assign edges, and basically we ask questions like, can D point to H2? And that's certainly the case through this path. So basically, the computational problem you have to solve here is just transitive closure on the assign edges with this additional alloc edge at the end of the chain. Alex, can you not hear me? Am I not loud enough? Or yeah, right. So field-sensitive analysis adds a little twist to this. You also look for transfer through matching load and store pairs. So for instance, here you want to infer that D can also point to H2 because it has these chains that go through those matching load and store pairs. The key insight to do this here is that those two, what we call the base nodes, or the base vertices of the load store pair, have to alias, and alias is defined as intersection of points 2. So you have this mutual recursive definition of points 2 and alias. Points 2 needs alias to compute those paths, but alias is also defined with respect to points 2. And the theoretical framework to represent this computational problem is context-free grammars, because you're essentially looking for paths where I can describe the pattern or the words that is formed by the labels on the respective edges with a context-free grammar. So it's context-free language reachability. So for this, standard algorithms exist. There's one by MySQL Reps, which is about 20 years old, but they have cubic complexity, which limits what you can do with them in practice. So the algorithm ID we have is essentially we want to drop the store load edges. If we find matching pairs, we want to replace them by, well, additional assign edges. We call this bridge edges, and therefore the entire set of bridges we call this a bridge oracle. Doing this in a way that makes it fast is actually quite difficult. It's actually as difficult as the original problem. But what you can relatively easily do to come up with an over-approximation at this stage. So later on, we need a refinement step to certify those edges, to establish their correctness, and to get rid of spurious edges we introduce in step number 2. This idea is actually not new. It's actually more or less the approach that was suggested 10 years ago by Sridharan, Dyck, and others in this OOSPLA 2005 paper. However, we make 3 changes. We use a new vehicle for computing transitive closure. We use a more precise oracle, and we actually make this approach precise. So I show later on examples that this original approach suggested in this paper does not reach full precision, whereas our approach does. So the bridge oracle, so the idea is a very, very simple one. So you have this matching load and store pair, so A and C may alias because you have this assign edge between them. So essentially you want to insert an additional bridge edge, which is semantically just an additional assign. So finding good bridge oracle, there's always this trivial approach where you just pair up all loads and all stores, but you quickly get combinatorial explosions, so that's something that's not going to work. The next thing you can look for is you can match loads and stores for the same fields. That is what Sutaran and others did in this 2005 paper. Or you can use an approach that can be roughly described as a Steingart-style analysis where you compute may alias without looking into points too, and that's what we use. So we roughly follow an approach suggested by Zhang and others in their PLDI 13 paper, and that produces a rather precise oracle. So a typical value we get is about 70%, and detailed data for this are in the paper. So this approach works as follows. So in the first step, we componentize the graph. So if you have a graph like this, sorry, the shading doesn't come through very well, so hopefully you can see that there's a component here. It looks very light. We start at that first traversal at the heap allocation nodes, and everything we hit, all the variable nodes we hit, are grouped into one component. So if you do this for this component, then we eventually traverse into a vertex that is already in a component. In this case, we just match it. So we essentially build weakly connected components, which can be done in linear time. So it's very, very easy to do. So the intention is that component membership over-approximates may alias. Yeah, as you can see here, we have all those nodes are connected with assigns, so say may all alias. So I have a simple example here which shows a little bit the recursive nature of the algorithm, and I use it as a running example through the slides. So in the first step, we would come up with this set of initial components. We refer to this as an initial component cover. Right. The next step is folding, and so this is ID from this PLDI 2013 paper by Zhang and others. So they worked on Dyck grammar. So essentially you have a situation like this, where we have a component. Remember that those components over-approximate may alias, and then we have a matching load and store pair here. And what we essentially do there is, because that over-approximates alias, we assume that there is another assign edge here, which kind of shortcuts between this matching load and store pair. So we introduce this, and because we have this assign edge, we also merge these components, and that's this idea of folding. So we call it folding because you have this kind of triangular structure. You kind of collapse together at the bottom. That's a very intuitive way to think about this. You might think about this as a pivot of the structure. So we merge components together in this step, but in a way that's just a vehicle for us to compute those bridge edges. So the components themselves, after we have done this, we actually forget about them. We don't need them anymore. So that might be a technicality, but one of the key insights to turn this into an effective algorithm was actually not just to use bridge edges, but also introduce additional vertices. And the reason is that very often you pair loads with multiple stores or stores with multiple loads, so that's a many-to-many relationship. So by having those additional bridge vertices, you can very, very effectively do this by this avoiding combinatorial explosion during this step of the algorithm. So in this example here, it would work as follows. In the first iteration, we would actually do this fold here and infer this edge, and then the second iteration, we would infer this edge. So it's a very, very simple recursive process of doing this. There's a source of imprecision there, and it's an example that showcases this a little bit. So because in this initial step, when we build this kind of components and fold them together, we ignore the direction of the edges. And therefore, we get situations like this, where we have those two base pairs, they end up in the same component, so we add this bridge edge, but it's a spurious bridge edge, because A and C may never alias. So the underlying problem really with this component merging approach is that components are based on an equivalence relation, which is transitive. However, may alias is not transitive. So that's the underlying problem that leads to an imprecise over-approximation. So therefore, we would like to refine this. So there are different ways of refinement strategies, which can be roughly classified as top-down and bottom-up. So let's talk about this here. So in a top-down refinement strategy, what you do is you first create a points-to index from all assigns and all bridge edges. and you make a very optimistic assumption that all the bridge edges are okay, and you just try to beat out the ones that are not okay, the spurious ones. And the way you try to find them is that for each bridge edge, you look for the matching load store pairs, the base nodes, and look whether they may alias with respect to your index. And sometimes you find cases where that's not the case, and you just remove them, and then you repeat this in the next iteration until you reach a fixed point. The beauty of this approach is actually that you always have an over-approximation. And because our problem is not very precise, you can, for many analysis clients, live with an imprecise solution because it doesn't really change much, right? So you can stop at any time. For instance, you can go in with a certain time budget in demand-driven analysis. Stop at any time. You always have a useful analysis, a useful index. It just gets better if you invest more time and refine further. You can also do it the other way around. You start with a points to index, which you just compute from the assigned edges, ignoring all bridge edges. And then you go for all the bridge edges, you look which ones are valid with respect to the index, add them to the set of assigns, and recompute the index. And you will also reach a fixed point. And the fixed point is actually sound. The proof is in the paper. But you can't really stop halfway through because then you have an unsound index. So it's not very useful. So the real interesting question is whether the two fixed points are the same. And that's maybe a minor contribution of our papers, that we gain some understanding about the nature of those fixed points and that they are in general not identical. And here's a very simple example. So in this in the top-down refinement, think about you have this bridge edge and you want to refine this. So you ask whether V2 and V4 may alias. Well, they may alias because V2 can point through this assign edge to H1, and V4 can also point to H1, but with the help of the bridge edge. So in a way, the structure becomes self-supporting or self-referencing. We haven't found exactly problem situations like this in real-world problems. However, we did find situations where you have sets of bridge edges which are mutually supporting. Jython, for instance, and some of the Decabo data sets have structures like this. So the question is now, does it matter? Because if we measure the precision of top-down versus bottom-up refinement, we find that the precision with top-down refinement is very, very high. So why should we care? Well, to put it, we found an example here in Decabo 2006. Plot actually has a very, very low precision if you use top-down refinement. And now that's really a matter of known unknowns to cite Donald Rumsfeld. So you don't quite know what you have if you do analysis on a program, whether it's the plot, which is unlikely, or whether it's one of the other programs that behave nicely where you could also use top-down refinement. So refinement in our running example. So in the first step, you would refine this edge, and in the second step, you would refine this edge and confirm and certify it. Okay. So essentially, at the end of the process, you could drop all load store edges and just recompute the points to index with a plain transitive closure algorithm. At this time, it's fair to ask whether we did anything useful in terms of complexity and performance, because it's not quite obvious, because we really transformed a context-free language reachability problem into a transitive closure problem. But the complexity is more or less the same. So the complexity of both is standard algorithms are cubic, and the best algorithms you find are somewhere in this space between quadratic and cubic. And algorithm people really, really struggle hard to push this down further, but are not making much progress. So the algorithm used for transitive closure actually is a very simple algorithm, which actually has cubic complexity. But we choose it based on a study of different algorithms available and on the topology of the graphs we are confronted with when we do points to analysis. So it's an algorithm by Nutella, which is more or less just a modification of Tarchan's algorithm to detect strongly connected components. So in a way, the situation is actually even worse, because you can come up with an example, which is kind of ladder, where you say, well, we essentially only have store and load edges, and we have this structure where you actually need n, well, more precisely, n divided by 3, but this constant factor in terms of complexity doesn't really matter, n steps to refine this entire structure. So at each step, we have to compute the transitive closure. So we didn't do anything good in terms of complexity, because we actually made it worse, and we managed to make it worse. Okay, but first observation, how many iterations do we need in practice? And that's really now a reference to the topology we find in points to graphs. Well, we did some measurements here, and it turns out that the number is constant low. And that is really just empirical data now that comes out of the analysis of data sets. And so The highest complexity is in some of the Carbo programs where you need 8 refinements to reach the fixed point. On the JDK, you need only 6. So there's no indications that this depends on the size of the program. That's the core insight. It depends on the structure of the program. And then, of course, typing and certain design patterns used in programs really limit this number. So we can assert that this is bound by a small constant. So that brings us back to cubic complexity. The next argument is on transitive closure. So the transitive closure algorithm we are using is cubic because you have to push reachability information. Worst case scenario n, you can reach everything through all edges. Worst case scenario, you have a dense graph with n square edges. So that is how you get to this cubic complexity. But because our graphs are extremely sparse, as you can see here, those are the vertices, those are the edges, they're almost identical, we come, in a way, back down to linear, right? Because it's a very, very sparse graph, and we don't get anywhere near this worst case complexity scenarios. For the pre-analysis, I cut this a little bit short. Okay, so sorry, that's the second argument here. That is a number of reachable sets. So that's the percentage of sets of a size less than 10. So it means that the sets we have to push through the edges are actually very, very small. So as a pre-analysis, we can make a similar argument based on the complexity analysis in this Zhang paper. So in practice, we have n log n complexity. So we are near linear in praxis. So implementation. There's implementation which is available in open source. I have to rush a little bit through this now, running out of time. We used the Carbo 2009 dataset. We had Oracle implemented or provided by an Oracle internal engine. So Oracle sponsored this project. I'm not sure whether I mentioned this. We compared it with 3 alternative implementations or algorithms. So we implemented Melsky reps, Sridharhan Fink's difference propagation algorithm, logic blocks, cross-tested them for false positives and false negatives to experimentally confirm soundness and precision. That is the size of the index we are talking about. I mentioned this number earlier, so we have 1.5 billion records we have to compute. That is probably the main result, which is also referred to in the title. That's the runtime. So Melsky reps and difference propagation both timed out on the JDK. We can create an index on this very notebook in 40 seconds with a very modest amount of memory. So with 3 gigabytes of heap allocated to the Java virtual machine. Logic blocks can also compute this, but logic blocks takes about 50 minutes or so. So logic blocks was the second best in terms of performance. Has, of course, other advantages because you can script it. Yeah, so that is all hard-coded in our approach now. So query time, so we don't make any compromises by the query times, at least not for for single source, single sync queries. Single source all sync queries are a little bit more expensive, and that has to do with the index representation, how we represent the result sets. Alias queries are also running in constant time. So breakdown of the steps, you kind of see the 3 steps here: componentize, folding, and refinement. And you see it on the JDK on the largest data set. Completely surprisingly, the one step that has the theoretical worst complexity of the overall algorithm is actually running the fastest. That's a really surprising result. Yeah? So, and that concludes my talk. There's a link actually to the software if somebody's interested in this. It's also referenced in the paper. Yeah, thank you.
You still have 2 minutes.
All right.
Okay, questions?